When one speaks of gravity, one must first unlearn a habit so deeply rooted in the human mind that it feels almost like common sense. For centuries, since the time of Isaac Newton, gravity was understood as a force, an invisible hand reaching across space, pulling objects toward one another. The apple falls, the moon circles the earth, and the planets dance around the sun, all because of this mysterious attraction. It is simple, elegant, and, if I may confess, deceptively comforting, but nature, as it often does, whispers a deeper truth beneath this simplicity. The first crack in this classical picture appears when we begin to question, what is this force made of? How does the sun, across millions of kilometers of empty space, know that the Earth is there? And more importantly, how does it pull on it without any visible connection? This idea of action at a distance troubled even Newton himself, though he mastered its mathematical description with extraordinary precision. Now imagine, instead of forces acting across emptiness, that space and time themselves are not passive stages upon which events unfold, but active participants in the drama of the universe. This is the beginning of a different way of seeing, a way that eventually led to what we now call the general relativity. Let us perform a simple thought experiment, for imagination is the laboratory of the physicist. Picture a vast, stretched sheet, smooth and taut, extending in all directions. This sheet represents space-time, the union of space and time into a single fabric. Now place a heavy ball in the center of this sheet. What happens? The sheet bends, curves downward under the weight. If you now roll a smaller ball across this surface, it does not travel in a straight line. Instead, it follows a curved path, drawn inward, not because there is a force pulling it, but because the surface itself is no longer flat. This is the essence of gravity. In the language of mathematics, this idea is expressed as the space-time curvature described by the Einstein tensor g mu nu is equal to 8 pi g divided by c to the fourth power multiplied by the energy momentum tensor t mu nu. Do not let the symbols intimidate you. They are merely a compact way of expressing a grand story. On the left-hand side, the term G shmuv nu represents the curvature of space-time, how space and time bend and twist. On the right-hand side, T shmuv nu represents the distribution of matter and energy, the contents of the universe, the constants G and C, the gravitational constant and the speed of light serve as the translators between these two realms. If I were to narrate this equation as one would tell a story, it would sound like this. The curvature of space-time is determined by the presence of matter and energy, or more poetically, matter tells space-time how to curve. Now consider what this means for motion. In the absence of any curvature, an object moves in what we call a straight line, the shortest path between 2 points. But in curved space-time, the concept of a straight line changes. Objects follow what we call geodesics, the natural paths dictated by the geometry of space-time itself. Thus, when the Earth orbits the Sun, it is not being pulled by a force in the traditional sense. It is simply following the straightest possible path in a curved space-time. This realization dissolves the need for gravity as a force. There is no invisible thread connecting the Earth to the Sun. Instead, the Sun reshapes the very stage upon which the Earth moves, and the Earth responds by following the contours of that stage. One might ask, is this merely a philosophical reinterpretation, or does it lead to real, observable consequences? Ah, here lies the beauty. This geometric view of gravity predicts phenomena that Newton's theory cannot fully explain. For example, the precise motion of the planet Mercury, whose orbit shifts ever so slightly in a way that puzzled astronomers for decades, or the bending of light as it passes near a massive object, a phenomenon confirmed during a solar eclipse, where starlight was seen to curve around the sun. Even light, which has no mass, follows the curvature of space-time. This alone tells us that gravity cannot be a simple force acting on mass. It must be something deeper, something woven into the fabric of reality itself. So we arrive at a remarkable conclusion. Gravity is not a force in the conventional sense, but a manifestation of geometry. The universe is not governed by invisible pulls and pushes, but by the shape of space-time itself. Mass and energy sculpt this shape, and everything else moves accordingly. In this way, what once seemed like a force becomes a story about structure, a quiet, elegant dialogue between matter and the geometry it inhabits. And if one listens closely, one begins to sense that the universe is not merely a collection of objects, but a living tapestry continuously shaped and reshaped by its own contents. If the first revelation was that gravity is not a force, but a manifestation of geometry, then the second insight follows with an almost poetic inevitability. What, then, shapes this geometry? What is the sculptor behind the curvature of space-time? The answer is both simple and profound: matter and energy themselves. Before this realization, space and time were treated as passive, a silent arena in which the drama of physics unfolded. Even in the refined worldview of Isaac Newton, space was absolute, unchanging, and indifferent to the events within it. But such a picture leaves an uncomfortable asymmetry. Matter moves within space, yet space itself remains untouched, unaffected, almost aloof. This, to a curious mind, is an incomplete story. Let us return again to imagination, for it is here that clarity is born. Picture space-time not as an abstract concept, but as a flexible fabric, capable of bending, stretching, and responding. Now place a massive object upon it, a star perhaps, or even something as familiar as the Earth. What happens is not merely a local disturbance, it is a transformation of the geometry itself. The presence of mass alters the very structure of space-time. But we must go further. It is not only mass that plays this role. Energy, momentum, pressure, even stress contribute to this shaping. The universe does not distinguish between these forms. All are expressions of energy in different guises. This grand relationship is encoded in the elegant language of the Einstein Field Equations, which can be narrated as the curvature of spacetime, described by the Einstein tensor, is equal to 8 pi times the gravitational constant divided by the speed of light raised to the fourth power, multiplied by the energy momentum content of matter and energy. Let us not merely read this equation, let us listen to it. On the right-hand side resides the energy momentum description of reality, but to call it a tensor is to hide its poetry behind technical language. Think of it instead as a complete inventory of everything that can influence space-time: energy density, the flow of energy, momentum, pressure, all the ways in which the universe contains and distributes its substance. It is, in a sense, the content of reality. Now, the constants, the gravitational constant and the speed of light, act as mediators. They ensure that the influence of matter and energy on spacetime is neither arbitrary nor chaotic, but governed by a precise and universal rule. If I were to narrate this equation in the spirit of a story, I would say the distribution of energy and matter determines the curvature of spacetime, or more vividly, matter tells spacetime how to curve. But let us not mistake this for a static command. This is not a one-time instruction, but an ongoing dialogue. Every star, every planet, every particle continuously contributes to the shaping of space-time. The universe is not a fixed sculpture, it is a living, evolving form. Consider a star quietly burning in the vastness of space. Its immense mass curves the space-time around it, creating what we perceive as a gravitational field. But this curvature is not limited to its immediate vicinity. It extends outward, influencing the motion of distant objects. Planets orbit not because they are pulled, but because the space-time through which they move has been shaped by the star's presence. Now imagine compressing that star further and further, increasing its density. As the concentration of energy grows, the curvature becomes more extreme. Eventually, one reaches a point where space-time bends so dramatically that not even light can escape. This is what we call a black hole, a region where the influence of matter on space-time reaches its most intense expression. Even more fascinating is the realization that energy alone, without mass in the traditional sense, can produce curvature. Light itself, though massless, carries energy and momentum and therefore contributes to the shaping of space-time. This subtlety reveals a deeper unity. Mass and energy are not separate entities, but different manifestations of the same underlying reality, a truth captured in another well-known relation. Energy equals mass multiplied by the speed of light squared. Narrated simply, this tells us energy and mass are equivalent. One can transform into the other. And since energy shapes space-time, mass, being a form of energy, naturally does so as well. Thus, the universe becomes a grand interplay between content and structure. Matter and energy are not merely inhabitants of space-time, they are its architects. They dictate its curvature, and in doing so, they define the very notion of motion, distance, and time. What emerges is a vision of profound unity. There is no longer a separation between things and the space they occupy. Instead, there is a continuous relationship, a feedback loop in which matter shapes space-time, and space-time in turn governs the behavior of matter. One might say that the universe writes its own geometry, and in this writing, every atom, every photon, every ripple of energy contributes a small but essential stroke. The cosmos, then, is not built upon a rigid framework, but upon a dynamic and responsive fabric, one that listens to the presence of matter and energy and responds by curving accordingly. If the second insight revealed that matter and energy sculpt the geometry of space-time, then the third completes the circle of understanding with a quiet but profound statement. Once space-time is curved, it does not merely sit there as a passive deformation, it guides. It instructs matter how to move, not through force, but through the logic of its own geometry. To appreciate this, we must once again loosen our grip on the familiar. In the world described by Isaac Newton, motion is dictated by forces. An object remains at rest or moves in a straight line unless acted upon. Gravity, in this view, is an external influence, a pull that constantly redirects motion. But in the geometric vision of the universe, this notion dissolves into something far more subtle. Imagine you are an explorer walking across a vast landscape. If the land is perfectly flat, your path between 2 points will be a straight line. But if the terrain is curved, filled with hills and valleys, your straightest possible path will no longer appear straight in the ordinary sense. You will follow the contours of the land, bending naturally according to its shape, not because a force is pushing you, but because the geometry itself defines what straight means. This idea, when translated into the language of space-time, gives rise to what we call a geodesic, the natural path an object follows when no external forces act upon it. In curved space-time, objects move along these geodesics. Mathematically, this principle is expressed through what is known as the geodesic equation, the second derivative of position with respect to proper time, plus the Christoffel symbol term that encodes spacetime curvature acting on the product of velocity components equals zero. Now, let us not be intimidated by the symbols. Instead, let us give them a voice. The position term describes where an object is in space-time, not only in space, but also in time. The proper time parameter represents the time experienced by the object itself as it moves along its path. The second derivative of position represents acceleration. In Newton's world, acceleration demands a force. But here, something remarkable occurs. The additional term involving the Christoffel symbols does not represent a force in the traditional sense. Instead, it encodes the curvature of spacetime itself, how the coordinate grid bends, twists, and changes from point to point. So when we narrate this equation, it says an object moves in such a way that its path is entirely determined by the curvature of spacetime, or more poetically, spacetime tells matter how to move. Notice what is absent. There is no force term on the right-hand side. The equation equals zero. This is the quiet revolution. Motion under gravity requires no force, only geometry. Let us return to a familiar example, the Earth orbiting the Sun. In the Newtonian picture, the Sun exerts a gravitational pull, constantly tugging the Earth away from its straight line motion, forcing it into a curved orbit. But in this new vision, the Sun does something far more elegant. It curves the space-time around it. The Earth, in response, simply follows the straightest possible path within this curved geometry. From the Earth's perspective, it is not being pulled. It is freely falling, moving naturally, effortlessly along a geodesic. What appears to us as an orbit is, in the language of space-time, the closest thing to a straight line. This idea extends even to light. One might think that light, having no mass, should be immune to gravity. But in this framework, gravity is not a force acting on mass. It is the curvature of space-time itself. And since light travels through space-time, it too must follow its geometry. Thus, when a beam of light passes near a massive object like the sun, its path bends, not because it is pulled, but because the space-time through which it travels is curved. This phenomenon, known as gravitational lensing, allows us to observe distant galaxies whose light has been bent around massive cosmic structures. Here, we see the universality of the principle. All objects, massive or massless, obey the same geometric law. They follow geodesics. One might now ask, if everything simply follows its natural path, where do forces fit into this picture? The answer is subtle. Forces still exist, electromagnetic forces, for example, but gravity, in its essence, is no longer one of them. It has been reinterpreted as geometry itself. This shift is not merely a change in description, it is a transformation in understanding. It tells us that motion is not imposed from the outside, but arises from the structure of space-time. The universe does not push objects along, it provides them with a stage whose shape determines their motion. And so the story comes full circle. Matter and energy shape space-time, and space-time, in turn, guides matter and energy. It is a dialogue, a continuous exchange, a cosmic conversation without beginning or end. In this light, the motion of a planet, the fall of an apple, even the path of a ray of light, all become expressions of the same underlying truth, that to move is to follow the geometry of the universe. There was a time when the universe was imagined as a grand but static stage, unchanging, eternal, and indifferent. The stars were fixed like lanterns on a celestial dome, and space itself was thought to be an infinite, rigid emptiness within which all events unfolded. Even the most refined formulations of classical physics carried this quiet assumption that the universe, at its deepest level, simply was. But the equations we now contemplate, the profound Einstein Field Equations, whisper a very different story. They do not describe a static cosmos, they describe something alive, dynamic, and capable of evolution. They tell us that space-time is not merely a backdrop, but a participant, one that can stretch, ripple, and even tremble. Let us once again give voice to the central equation, the curvature of space-time described by the Einstein tensor plus the cosmological constant multiplied by the metric of space-time is equal to 8 pi times the gravitational constant divided by the speed of light raised to the fourth power multiplied by the energy momentum content of matter and energy. Now, we have added a new character to our story, the cosmological constant, but let us not rush past it. Each symbol here carries meaning, like actors in a cosmic play. On the right-hand side still resides the energy momentum description of the universe, the content of reality. On the left, the Einstein tensor describes the curvature of space-time, but now the additional term introduces something subtle and mysterious, an intrinsic tendency of space-time itself to expand or contract, even in the absence of matter. Narrated in simple language, this equation now says, the curvature of space-time is determined not only by matter and energy, but also by an inherent property of space-time itself. This addition transforms our understanding in a profound way. It suggests that the universe is not merely shaped by its contents, it possesses its own internal dynamics. Let us imagine for a moment an empty universe devoid of stars, galaxies, or particles. One might expect such a universe to be perfectly flat and motionless, but the presence of the cosmological constant tells us otherwise. Even emptiness is not truly empty. It carries a kind of latent energy, a quiet pressure that can cause space-time to expand. This idea leads us naturally to one of the most astonishing discoveries in modern cosmology, the expansion of the universe. Observations reveal that distant galaxies are moving away from us and from each other, as though the fabric of space itself is stretching. This is not an explosion from a central point, but an expansion of space-time everywhere in all directions. The mathematical expression that captures this behavior arises from cosmological solutions of the field equations, often written in terms of the scale factor. The square of the expansion rate of the universe is equal to a combination of the matter density term, the spatial curvature term, and the cosmological constant contribution. In words, this equation tells us the expansion of the universe is governed by its energy content, its geometry, and an intrinsic property of spacetime itself. What emerges is a vision of a universe that evolves. It can expand, slow down, accelerate, or even collapse depending on the balance of these factors. The cosmos is no longer static. It has a history, a present, and perhaps a destiny. But the dynamism of space-time does not end with expansion. It can also ripple. Imagine a massive event, a collision of two black holes, for instance. The immense energies involved do not simply rearrange matter, they disturb the very fabric of space-time. These disturbances propagate outward as waves, much like ripples on the surface of a pond. These are gravitational waves, subtle oscillations in space-time itself, predicted by the field equations and now observed directly. They are described in simplified form by wave-like equations, stating that small perturbations in spacetime propagate as free waves. Narrated simply, this means disturbances in spacetime travel as waves, carrying energy across the universe. Thus, spacetime is not rigid, it is elastic, responsive, alive with motion. From the birth of the universe in a hot, dense state to its ongoing expansion, to the faint whispers of gravitational waves passing through us at this very moment, the cosmos reveals itself as a dynamic entity. It breathes, it evolves, it resonates. And perhaps the most humbling realization is this: we are not separate from this process. Every atom in our bodies, every thought in our minds exists within this ever-changing fabric. We are, in a very real sense, participants in the evolution of space-time. So the fourth insight stands before us, not merely as a scientific statement, but as a philosophical revelation. The universe is not a static construction, but a living dynamic structure, one that is continuously shaped, reshaped, and set into motion by both its contents and its own intrinsic nature. In this grand unfolding, space-time is not the stage,